Previously, I had finished up by observing that the special case of acceleration being a constant was something that we would want to look at, because even if real-world acceleration isn't constant for a lot of systems, you can often do a very accurate job of modeling it at least as segments of constant acceleration. And the math for constant acceleration is much easier than the math for not constant acceleration. So this is a good starting point. But I do want to be clear, our condition for uniform acceleration and everything I'm going to be doing in this video is going to depend on the assumption that the acceleration is a constant. And this is a special case. Now we do have to be very careful about things because, for instance, if, say, somebody drops a ball, you can model the falling ball as constant acceleration in a lot of circumstances. But if you take it all the way to when it hits the ground, when it hits the ground, it was going really quickly downward. It was picking up speed downward, so its acceleration was downward. But then when it actually hits the ground, it winds up having to lose an awful lot of speed downward, which means the acceleration will be upward. So you have to be very careful about things like that. In a situation like that, often what you have to do is say, I'll look at it just the split second before it hits the ground. We'll be worrying about that in later videos, but I mention that just to say that you do have to treat this with care and realize that even in situations where it looks like the acceleration is a constant, you may have to sit and ask yourself carefully, is it really? But with that warning aside, let's go ahead and take a look at what that means. So I will go ahead and make a velocity time graph for a typical case of uniform acceleration. Now, to have uniform acceleration, that means the slope of the velocity in a velocity time graph needs to be a constant. So the slope here is equal to the acceleration. We'll just observe that. And so this can give us our first starting point for some of the, will be the first of four special equations that come out of the assumption of constant acceleration, which I like to call the gang of four. So first we can just start by observing the acceleration is the time rate of change of the velocity. And since we're assuming the acceleration is a constant, I don't have to write it as a derivative. I can just keep it as change in velocity over change in time because the slope never changes. So I can rearrange this and have that delta v is equal to a delta t. And then if I put in what that is, the change in the velocity will be the final minus the initial. I'll leave the change in time the way it is because I'd say probably about 85, 90, and more like 95% of the time, you're going to make the initial time 0 anyway. And so the time and the change in time will often, but not always, be numerically the same. So if I rearrange this to get the final velocity, I get the first of my gang of four. So what we get is the final velocity is equal to the initial velocity. So the velocity you finished with is equal to the velocity you started with plus the acceleration times the time of the motion. And I will number this equation number 1 just for consistency in my notes. Now the next place that I would like to go is say, well, what about if we're interested in finding how far we went? Okay, we can do that by finding the displacement. And we remember that the displacement, so let's say this is my elapsed time delta t. This would correspond to my initial velocity here. That would correspond to my final velocity there. my displacement will be equal to the area under this curve, like so. Now this shape is a shape we hopefully remember from geometry. It's a trapezoid. Okay, maybe not. But it is a trapezoid, and the area for a trapezoid is something that we can look up. And so we'll say that the displacement is equal to the area under the curve. And the formula for the area of a trapezoid is the length that doesn't change times the average of the lengths that do change. So what changes here is this height here is v initial, that height there is v final. So we use the average of those, so it'll be 1/2 v initial plus v final. And then the length that doesn't change in our trapezoid is this, so delta t. Okay, if you're not 100% thrilled with that, I can kind of justify it a little differently. And just say, since the velocity is changing steadily, in this particular case, the average velocity will be perfectly in the middle between the initial and the final. So then this, effectively what we're doing is we're taking this area here and sticking it in over there like that. And so then this becomes the average velocity times the time. So we can argue it that way as well. And we remember that the displacement is going to be my final position minus my initial position. So if I rearrange this to get the final position by itself, the final position will be the initial position plus the average velocity times the elapsed time. And I am cryptically going to number that as equation number 3. Yes, I know I skipped to number 2. We'll be back to it. So to get equation number 2, what we can do is take, here we go, and take the final velocity I got here and stick it in. Ooh. Final velocity I got here and stick it in there. So now what's that doing for me? Well, something that we'll catch on to is this equation doesn't have a position in it. This equation doesn't have an acceleration in it. If I substitute the velocity here, I'll make an equation that doesn't have the final velocity in it, which is where we're going with that. So making that substitution, I'll have x final equals x initial plus 1/2 times v initial, and then substituting for the v final, I'll have another v initial plus a delta t, and then I have to times all that by delta t. Okay, so I've got two v initials here. So this is x initial plus 1/2 times 2 v initial plus a delta t. Now, if what I go ahead and do is I'll multiply both of these terms through by delta t. So this would give me a 2v delta t. And then when I times that by half, I'll just have v delta t. So I'll have x initial plus v initial delta t, just multiplying the 1/2 and the delta t against this term. Now if I multiply the 1/2 and the delta t against this term, I'll have plus 1/2 a times delta t squared. Notice I put this in quantities. And this is because, just as a side note here, this is because delta t squared is not the same thing as delta t quantity squared. This would be read as the change in t squared. This is the change in t quantity squared. So here you first calculate the change and then you square it. Here you calculate the square and then you figure out the change in what the square is. So these two things aren't the same thing. So when you're doing delta t squared, you do need to do it in parentheses. All right. And then we can go back, and playing the same game here, we can get rid of the time between the equations. So if I go back here, what I'll do is I will solve equation number 1 for delta t, and then stick it back into my equation number 3. Now that I have my equation number 2 here. So following on that thought, we'll first need to rearrange my equation 1 to get in terms of delta t. So I'm just going to rewrite equation 1 here real quick. V final equals V initial plus A delta t. I need to rearrange that. A delta t is V final minus V initial, or delta t is V final minus V initial over A. So now that I have that, I can stick that into here. So this will give me x final equals x initial plus 1/2 V initial plus V final times, this will be V initial minus V final minus V initial over A. Now, let me clean this up just a shade. So this will be x initial. We'll just put this, say plus, and we'll just put that all over 2A. If I swap these, I'll have V final plus V initial times V final minus V initial. And I remember that when I multiply these two together, that's going to give me V final squared minus V initial squared. So I'll have that x final is equal to x initial plus V final squared minus V initial squared over 2 times the acceleration. And that is the fourth of my gang of 4. All right. So it's probably worth taking a moment to just rewrite these all into one clean table. So let's just do that right now. So here's my relation. And then I'm going to make another column where I just write missing, and I'll explain what that means in a second. And so we'll have V final equals V initial plus A delta t. X final equals X initial plus V initial delta t plus 1/2 A delta t quantity squared. X final equals X initial plus 1/2 V initial plus V final delta t. And finally, V final squared equals V initial squared plus 2A X final minus X initial after I rearrange what I had before. This is usually how people write it. Okay, so if we take a look at these, we'll see, like I was alluding to earlier, that each of these is missing one of the 4 key kinematics variables, which are position, velocity, acceleration, and time. This one does not have position in it at all. This one does not have the final velocity. The initial velocity is there, but it doesn't have the final velocity. This one here does not have the acceleration, and this one here does not have the elapsed time. And I mentioned this because it'll help us to figure out when we have kinematics problems, situations where we can model the acceleration as a constant, it'll help us to pick which equation we want. By the way, a lot of textbooks don't give us this last one. And the reason they don't is what they're afraid of is if you just start grabbing random equations and using them as you substitute one into another, if you have all 4 of these, you can get into a situation where if you make enough substitutions, you can just end up getting absolutely everything to cancel, and you're left with 0 equals 0, which, while true, isn't terribly useful. But I view that as being at the cost of being able to directly handle situations where the time is missing. And so my attitude is, if you can identify what is neither asked for nor given in a problem, you can use that to immediately pick the correct relation for your situation. Okay, and this is probably as good a time as any for me to go over my model of how I like to solve physics problems. And it goes by the mnemonic STAR. So the S stands for situation. So here, absolutely the very first thing you should do looking at any problem is to draw a picture. I can't stress enough how much this helps you to visualize what's going on and to get some sort of understanding of what the problem is all about. And trust me, even with the most complicated of problems where you couldn't even imagine that physicists could somehow draw a picture, we actually come up with ways of drawing pictures just to help us visualize at least aspects of the problem, even if we can't do the whole thing. By doing that, it can save a lot of time figuring out what you need to do. So, draw a picture. Make sure you understand what's going on. And you'll also definitely want to know, what are they asking for and what have they given you? Once you understand that, you can go to the next step, what I call tools. When you know what you're being asked for and what you're being given, using prior experience plus what we're learning here, hopefully you'll be able to pick the most fruitful relationship that will lead you to a good answer. Now, what this does not mean, and I cannot emphasize enough what this does not mean. This does not mean just randomly grabbing equation 17.34. I don't even know what equation that is. I don't know what book you're using. But don't just up and randomly grab an equation that has what looks like the right letters in it. And that's because in a book, a lot of times they're working on specific examples or specific situations. And unless you know for sure that that situation applies to you, you will just end up getting yourself the wrong answer because you misapplied a relationship. You applied a relationship to a situation that wasn't valid for what you're looking at now. So this is why I'm always a fan of starting with relations with broad applicability. Things that are always true, or if they are special cases, like the case of acceleration being a constant, are true an awful lot of the time, and it's easy to check whether that's a valid assumption. I would not just pick the solution that was the answer to problem 17 and hope that that works for problem 18. It might not, and you wouldn't know. So start with things that are always true, and then what we will do is we will start from things that are always true and drill it down to the situation at hand. So that gets us to the answer stage. So these first 2 steps, we're mostly just doing physics, thinking about the situation, figuring out what laws of nature apply. This step here is mostly a diversion into the land of math. Once you've taken your physical principles of broad applicability, what you'll then do is mathematically manipulate them until you get what you need on the left-hand side of the equal sign and what you are given on the right-hand side of the equal sign. And by the way, don't put in numbers right away. Yeah, I'll bend that rule for the number 0, but that's about it. Otherwise, my mantra is letters good, numbers bad. And why is that? Well, there are actually many reasons. One is if you just up and stick the numbers into an equation right away and then try to manipulate it around for what you want, in my experience, you are much more prone to transcription errors. It's really easy to turn numbers around. It's really easy to drop digits. And assuming that you even catch your mistake, it's basically almost impossible to go back and find your mistake. So instead, I always strongly urge you, just keep it all as letters. There are other reasons for that, and that's sometimes you end up with situations where you have to keep analyzing substantially the same situation over and over. I'll just mention that when I was first learning this material, my professor decided that it would be really fun on one of the exams to give us a problem that was fairly straightforward to solve. And then he basically said, okay, part B, rework the problem for these initial conditions. Part C, rework them for these initial conditions. Part D, rework them for these initial conditions. Part E, rework them for these initial conditions. Part F, Part G, Part H, Part I, Part J. Yeah, we went that far. The students who just up and stuck the numbers in right away, by the time they got to Part J of problem number 1, the professor called time. They never got to the other problems on the test. On the other hand, if you did it all as letters, that meant that you solved it once, and it was just kind of tedious to have to keep punching in new numbers in your calculator, but you had the right functional form. Now, that's probably a bit on the punitive side, but it is when you're doing, say, writing computer code or something like that, it's something worth keeping in mind. Another reason is to avoid round-off error, and this can be a big deal, especially now that we're having to worry about building things to ever tighter and tighter tolerances. The problem with round-off error is that you would think as you're doing each step in a problem, if you get in the habit of doing doing a step and you put the numbers in your calculator and then you kind of round it off, you round it off to some number of digits and you put it back in and you crank in the next step and so forth. If you do that, you would think that, half the time you're rounding up, half the time you're rounding down, what's the big deal? Well, it turns out that statisticians have shown that once you start doing that, the answer tends to snowball away from the right answer. You don't tend to have it round back toward you. It just keeps rounding away from what's right for the most part. It can go both ways, but it tends to round away from the right answer. And I've seen it where people have mechanically done a problem correctly, but been off by 20%. Well, if you're off by 20% in some part of a calculation, depending on what you're designing, that might not be good enough. And then you might discover that when you prototype it, that you had a failed prototype. And that will cost time and money. It's also worth pointing out, for instance, there are certain classes of drugs where you give a patient 1% too much, you kill the patient. But if you give a patient 1% too little, you don't treat the disease. Being off by 20% there is not going to have a good outcome for the patient. So generally, there are other reasons, and I'll kind of get to those as we go along working things. Honestly, the one that I find the most useful is that when I make a math mistake, it's easier for me to figure out where I messed up. Because if I do it just by numbers, I'll have to start all over again. But as we go along, I'll keep bringing out more of it, but get in the habit of solving everything as letters until the bitter end, with the exception that it's generally okay to stick in the number 0. And then finally, review. Part of what makes physics different from a math class, even though calculus was invented in order to make physics easier to do, is that for us in physics, the letters actually stand for things. And they're describing things that are happening in nature. So for instance, when you substitute in your values, not only should you put in the numbers, you should also plug in the units. So the very first thing is when you plug in the units, you should be asking yourself, do the units check? If they do, that's not a guarantee that you didn't make a mistake. But if the units don't match up, that's definitely a guarantee that you did make a mistake. If you're expecting a velocity and you get units like meters squared per second, you know that that's not a velocity, then you flat out know that you made a mistake somewhere. And how the fact that in this case you ended up with an extra power of length will actually let you help go back and look at your math and see where you might have messed up. And the other thing is we do live in a physical universe that we know things about. So you should also ask, is the answer reasonable? If you're solving for, say, the speed of some car doing a quarter-mile drag race and you get that the car is going at 10% of the speed of light, that's not going to be too reasonable. And that would again indicate that you almost certainly made a mistake. All right, so let's just work through a couple of problems here just to get a bit of a feel of it. And since we've been talking cars, let's go ahead and take a look at a couple of cases here. So first one I'm going to do, so I'm just going to draw my picture while I'm explaining the problem, is I'm going to say that I had a car travel 100 meters. So I just arbitrarily decided to make x initial equal to 0. I'm allowed to do that. So we say the car traveled 100 meters. So there's my car 100 meters down the road. And we'll say that it traveled that 100 meters in 5 seconds. So I drew a little clock just to tell me that 5 seconds elapsed. So since that's an elapsed time, I can go ahead and say if I want that I can set t initial to 0 seconds, making t final 5 seconds, but I'm not too worried about that here. Go ahead and say that the final velocity is 30 meters per second. And what we're being asked to find is what was the initial velocity of the car. So there's my situation. I drew the picture and I identified what I knew and what I was being asked for. So in this case here, it's like, okay, I'm being asked for the initial velocity. I have the final velocity. And what I want to find is some tool that will let me connect all this information together. Well, we're tacitly assuming that this is uniform acceleration, because that's the section we're working on here. So, in fact, we can even just say the car accelerated uniformly. So what I like doing for identifying what equation to use is figure out what am I missing. So in this case here, what I mean by that is the variable that is neither, the kinematic variable is neither asked for nor given. Well, I'm asked for the initial velocity, I'm given the final, I'm given the time elapsed, I'm given the initial and final positions. What is neither asked for nor given is the acceleration, so we'll say that the acceleration is missing. So then that means my tool is going to be the equation that does not have an acceleration in it, namely this one right here. So we'll just say, oops, let me give a little bit of room over here. So we'll say x final equals x initial plus 1/2 v initial plus v final delta t. All right. So that's my tool, and now let's proceed to find the answer. Now, one of the things I did say is, although letters good, numbers bad, it is okay to bend the rules with 0. So I'll put in that my initial position is 0. I'll put that in right away. That's fine. And I just want to identify what it is I'm being asked to solve for here. I'm being asked to solve for v initial. So at this point now, we can kind of just put our physics brains on pause for a second. We're just doing algebra to get delta t on the left-hand side and everything else on the right-hand side. So, alrighty then, I can multiply everything by 2, so that'd be, whoops. So that would be v initial plus v final delta t equals 2x final. And then I could divide through by the stuff in the parentheses. Oh, sorry, no I don't. I can divide through by delta t, my bad. So v initial plus v final, v initial plus v final equals 2x final over delta t. And then finally I can get what I want, which is the v initial on the left all by itself. This will be 2x final over delta t minus v final. All right. So now we can go ahead and put in the numbers along with their units. And we need to make sure that the units work out. So this will be 2 times 100 meters over 5 seconds minus 30 meters per second. Now when I add or subtract two quantities, they have to have matched units or it'll be meaningless to try to add them. Here I have meters, I'm dividing by seconds, so this whole thing here is meters per second. That's meters per second. So when I add and subtract, they have matched units of meters per second, which is good. And it's also what I'm expecting because I'm solving for a final velocity. So I have, let's see, this is going to be 200 over 5 is 40, minus 30 is 10. We had meters per second, so everything's in meters per second. So I have that my initial velocity is 10 meters per second. And if so you should be asking yourself, well, is that a reasonable thing? Well, just as a very crude way to ballpark it, one way I can think of is that there are people who can run 100 meters in 10 seconds. They're generally very athletic, but there are people who can run 100 meters in 10 seconds. So that means that they're going 10 meters per second. So if a person can go 10 meters per second, it's certainly totally plausible that a car could go 10 meters per second. So we feel pretty good about this answer. Again, it's not a guarantee that we're right, but if I had solved this and got 1 billion meters per second or something like that, then I would definitely be going back and triple checking my work. All right. Let's try another one. So in this one, again, it'll be a car. So again, I can just say we're starting at 0. And we'll say that initially my car is going at 100 meters per second, which is really fast, but it is race car kind of speeds. So I said a car, I didn't say what kind of car. And the car starts really slowing down and it travels 100 meters. And at the end of 100 meters, it hasn't come to a stop, but it is going at 40 meters per second. So it's going slower than it was before. All right. And what I want to know is what is the acceleration. Now, believe it or not, we can milk a little bit more out of this. So we're already kind of into the land of tools in that we can start to at least get an idea of what the sign of the acceleration is. Can you figure out what the sign of the acceleration is? Go ahead, pause the video and get back with me on that. Okay, so hopefully you worked out that the acceleration is negative. And we get this because we're going to the right quickly, and then we're going slower to the right. So if we're going to the right and slowing down, that means the direction of my acceleration is to the left. So since the acceleration is pointing to the left, that means that my answer is negative. So before I've even done a lick of math, I've already at least figured out that the acceleration is negative. All right, so now we need to figure out what tools we're using. Again, we were told that this was a uniform acceleration, so we can go ahead and use the gang of 4, and we need to figure out which one. So here, the variable that's neither asked for nor given is the time. So we are missing delta t. So in that case, we will use v final squared minus equals v initial squared plus 2a x final minus x initial. And once again, it's okay to put in numbers that are 0, but that's the only number you should ever put in right away. And again, I'm just going to identify what we're trying to solve for here, the acceleration. All right, so we have a relationship where either it's the thing we're being asked for or it's something we've been given, so we're good to go. All right, so now we're into the land of just doing some math for a while. So the answer phase. So I get the acceleration by itself, so 2a times x final, that will equal, subtract v initial squared from both sides, so give me v final squared minus v initial squared, and then I can divide through by 2x final on both sides to get that a is v final squared minus v initial squared over 2x final. All right, so again here, let's go ahead and put in what the numerical values are. So we said that the final velocity was 40 meters per second. We'll square that. Minus 100 meters per second. We'll square that. And then we'll divide by 2 times 100 meters. Now, let's think about those units for a quick second here. So here, this term is meters per second. I'm not only squaring the 40, I also have to square the meter and I have to square the second. So that term is going to give me meters squared over seconds squared. So is this term. Add and subtract them. Add or subtract, we have to have compatible units. We're good. So the numerator here has units of meters squared over seconds squared. The denominator just has units of meters. Well, that's good. That cancels 1 power of meters to leave me with meters per second squared, which are the correct units for acceleration. So that, although it's not a guarantee that I didn't make a math mistake, it at least makes me feel a little bit better. All right, so now if you punch the numbers through in your calculator, you'll get minus 42 meters per second squared. And now you need to ask yourself, I'll do the units check. Yes, they do. We want meters per second squared. We have them. Is the number reasonable? Well, I mentioned that for the conditions we were being given, we were having to talk about a race car. And it certainly is possible for a race car to brake at 4 Gs. Puts an awful lot of strain on the driver's neck, but that's why they're being paid an awful lot of money to do what they do. So it is reasonable. And then even further, we can look and see 42, which of course we all know is the answer to the ultimate question of life, the universe, and everything. And yes, I am that big of a nerd that I would have written the entire question in order to get that answer. Alrighty. So there are a couple other things that I just want to look at briefly here. I want to talk briefly about free fall and about inclined planes. So, free fall. Unfortunately, books, in my opinion, get into this a little too early, but since it's basically every book gets into it, I'm going to have to bring up the idea of forces before we actually legitimately have forces. So I will just say here that for free fall, what we mean is that the only force in the problem is gravity. So in this case here, if the only force acting, we haven't formally defined forces yet, but I think we can at least just use our intuitive sense of it for the moment. We will see in a later video that if the only force is gravity, then the acceleration is minus 9.8 meters per second squared downward, so negative. And this is only if we are near the surface of the Earth. Now, what I would not want to see is I don't want to see people writing that the acceleration is equal to negative g, or making that kind of substitution. That leads to a lot of problems. The main issue here is that this quantity g, which you may or may not have seen in a previous lifetime, if you've seen it, what it is not is an acceleration. It's often misnamed the acceleration due to gravity in a lot of books, but what it really is a thing called the gravitational field strength. And so the actual correct units for G are newtons per kilogram, which we haven't gotten to yet, but have the same physical dimension as meters per second squared. Why it should be so I don't want people substituting that in right away. I would just as soon say, okay, if they're telling you that something's falling near the surface of the Earth, then you should write that it's 9.8. That means the acceleration is down, so negative 9.8 meters per second squared. Now, if it's near the surface of some other object, like let's say the moon, it'll be with the moon, it's about a sixth of that. And even for our own Earth, this number changes with altitude. Now, a general rule of thumb is if a creature or a machine can still breathe, so if we're at least at the point of flying at highest altitudes, then to two significant figures, it's okay to say it's 9.8 meters per second squared, or if you really want to use old money, 32 feet per second per second. However, by the time you get to, so that's in the range where people in aircraft operate, you get just not even that much higher. You get about 100 miles up to around the altitude of the International Space Station, which is not that high above the surface of the Earth compared to the size of the Earth itself. You're already at a point where its acceleration, if you were to drop an object from that altitude, it would accelerate not at 9.8 meters per second squared, but actually at 8.9. So it's kind of easy to remember because you can switch the digits around. You go even higher, say to the altitude of where a lot of communication satellites are located, and you're to drop an object from there, the acceleration would be 0.223 meters per second squared. So the main thing here is that this value of the acceleration actually changes with altitude. So I want you to be aware of that as well. So if you've seen forms of the gang of four where they just up and substitute in a negative g or something like that, I would expunge that from your brain. That creates more problems than it solves. Solve free fall problems normally, but just use it that they're saying that they're just giving you that the acceleration is 9.8 meters per second squared downward. So that's the one caveat. The other caveat is, say, if you have an inclined plane. We'll derive this later, but sometimes you see it in problems right away. So say if you got an object either moving up or down a ramp, it doesn't matter. There's more than one force acting on the object. And so the net combination of all of them will give you that the acceleration will be pointed down the ramp, and it will be equal to, in magnitude anyways, so I'll just say the magnitude of the acceleration will be equal to our 9.8 meters per second squared times the sine of theta, where theta is the angle of the ramp, like that. And yes, I draw my thetas like this. So just real quick here, this is a cursive Greek theta, I draw it like that. This is a cursive Greek phi, I draw it like that. The reason I do that is with printed thetas and printed phis, is they end up starting to look the same, and then you can't tell them apart. So for me to be able to tell them apart, I wound up just deciding to write them as cursive letters so that I couldn't mess them up. Okay. So if you run into problems with inclined planes, again, it's the same gang of four thing, but they're just telling you the acceleration is 9.8 meters per second squared down the ramp. And it'll depend on the context of the problem, whether you decide that that's a positive or a negative number. Then finally, you might ask yourself, what if the acceleration is not uniform? Oops. And there, if the acceleration isn't uniform, it's usually you're just going to have a case of the big sad. We can still get, so if I make a velocity time graph, for instance, here, if I want to know the acceleration at this point right here, it's still the slope of the tangent line. Because the acceleration is the derivative of velocity. And we can also go in the other direction, where if I have an acceleration time graph, I can go ahead and find the change in velocity by doing the area under the curve trick. So let's say you have something like the acceleration is doing this, and then this, So A versus T like that. This cross-hatched area here, oops, would be the change in velocity over this interval. In this case here, I'd probably break this into a square and a triangle, find the areas of both of those and add them together. Not something that I'm too stressed out about. The only situation I think really that you're apt to run into where you'll have accelerations changing in some way that isn't pretty. So here, this is something like the machine is just programmed to do this or whatever. But something where it isn't pretty is, say, launching a rocket. Because the rocket motors can produce a certain amount of thrust. Now, as rockets burn fuel very rapidly, and as they burn the fuel, although the thrust doesn't change, the mass of the rocket starts dropping. And in so doing, the acceleration will go up as a result, we'll see. It doesn't change in a super duper clean way, so doing these kind of drawings isn't going to really, doing this kind of analysis isn't really going to help there. It is something solvable, and you end up with Solovsky's first and second rocket equations, but that's for another day. Alrighty. So in the next video, we will go ahead and more seriously build up the formalism for vectors and coordinate systems, so that we can start transitioning to thinking about motion in more than one dimension. So we'll catch you over there.